just wanted to spend a minute on the motivation behind developing GDM. So as you look at the distribution system analysis set of tools, there is a lot of tools that exist today. So we've got Shift, ERAD, Disco, and a whole bunch of others as well that I couldn't list here, right? As we started to develop Cadet, one thing we realized was if we wanted Cadet to be interoperable, we wanted to be able to work with other tools. That is going to be difficult to do just because every single tool that we had within the distribution space, most of them were initially developed for a very particular project, which meant that they had their own interfaces and they also had their own model definitions as well, right? So every single time we had to map one tool to another or define these automated workflows, we had to build out these translations between these different data models essentially. In most cases, this was not easy, and most of these tools did not have capability to serialize and deserialize, right? Again, if you look at all of these tools, almost all of them work within Python, and once what we realized was there was a need to be able to define these data models in a way that is shared across all of this entire ecosystem essentially, right? So take out model definition out of these different tools, define them separately, and use that as a dependency in every single tool that we work with essentially. This allows to have greater interoperability, which means that we can set workflows between different models. So for example, Shift creates a GDM model. ERAD runs resilience analysis on a GDM model now, but that wasn't the case before GDM was defined, right? So what we've done within the last year and a half was kind of refactor a lot of these tools to make sure that they work within the GDM framework itself, essentially. So when we talk about interface requirements, we wanted the ability to be able to serialize and deserialize models that we have. Given most of our use cases require support for time series, we wanted to be able to handle time series efficiently. We wanted there to be helper functions that allow us to explore the model efficiently, easily, and we wanted the base model to be the base library to be agnostic to the energy domain, right? And out of this set of requirements, the infrastructure system package was born. As I said, this package takes a lot of inspiration from the Sienna models, the way Sienna does its data management, but we've built a lot of capability on top of this as well. Infrastructure system is a data store for components and associated time series. It's built for Python-based modeling packages. It stores components and data structures in an efficient manner. It supports unit conversions using Pint in Python, and it manages very efficient serialization and deserialization to and from JSON. So essentially, you're able to write to disk your models, and you're able to combine models back in memory from serialized models as well. And then there is support for automated handling for nested objects as well. So why is this important? Why do I talk about infrastructure systems? So the GDM-based model actually builds on top of the infrastructure system, right? The GDM is just a bunch of model definitions for the distribution system, whereas infrastructure system is agnostic to the domain itself, right? The infrastructure system library doesn't require you to work within the energy domain. One example I have for this is that the ERAD refactor that just recently did, we have a system that defines hazards. So we have a hazard system. In GDM, we have data models that represent the distribution system, and then there are other packages where we have defined systems that allows us to efficiently serialize and deserialize the systems and simulate their interactions. But the idea is that we have one library that allows us to handle all of these capabilities in an easy manner. So why grid data model? So there are other standards that exist as well. As we started on this, as we started to work towards building our GDM, we looked at other standards that already exist, right? One of them very popular is the SIM interface, the SIM interface, Common Information Model. what we realized that a lot of the researchers typically don't like to use SIM, and that is because of the way the nested structure it has. It's difficult to work with. We wanted a simple user interface that allowed us to users to work with models in an easy manner. But there are other features that we wanted to build out as well that SIM doesn't currently support. For example, a built-in validation layer that doesn't exist in SIM. So we wanted to use Pynetic models that allows it to validate singular models, but not just singular models. In GDM, we actually validate connectivity as well. So for example, you wouldn't be allowed to connect a three-phase load to a single bus system, a single-phase bus essentially, right? Things like that. So we have a lot of validation for not just component level validation, but validation of connectivity as well. That is missing from SIM itself. So in SIM, you can build a model that is not a valid power flow model. A validated GDM model is always going to be a valid power flow model. So that is one big difference. So we have built-in unit conversion for within the GDM models. We support serialization and deserialization. A couple of capabilities that I think are really powerful that we started to use for Cadet and for ERAD is the ability to track changes within the system as well. So imagine you've got a base model and then you've got some updates or changes happening on the system itself. In a contingency analysis, it might be there are assets that are outage, for example, right? And you want to track those changes as in a temporal manner. GDM supports all of these features, and I hope to go over some of them today. We provide you a connectivity graph as well using NetworkX. That is used for visualization, and that is used for a few algorithms as well that we'll talk about. We have built-in support for model reduction. So for example, if you have a complete three-phase unbalanced model, you want to reduce it to, say, a balanced three-phase system, or you want to just keep the primaries, take out the secondaries, we have built-in capability to do that as well. And then interoperability being the biggest thing here, right? GDM is used in several distribution modeling tools now. We've refactored Ditto, we've refactored Shift, we've refactored ERAD as well. So all of these different tools now work with GDM as the core model essentially. So if you're using GDM, you can define workflows that go from one tool to another very efficiently now.